In the last few videos, we moved to the position representation and discussed two sort of um, simplified models, the particle in a box or the infinite square well potential. And then last video, we went through the finite well potential, finite square well. Today, what we're going to do, we're going to build into this and get used to dealing with time dependence and different things in the position representation. But first, let's sort of recap and discuss a bit more about what we learned with those two square well examples. So start, we first looked at the particle in a box problem. So in one dimension, this is an infinite square well potential. So the potential is infinite, below for x less than 0, infinite for x greater than L. The box has a length L, and the potential is 0 inside the box. What we did was we looked at the energy eigenvalue equation, basically the Hamiltonian eigenvalue equation, and what we saw was that the energy of the quantized states, so the states get quantized, and the energy of each state goes as n squared and is inversely proportional to the length squared. And we saw that the solutions were essentially sine functions. And as you know, n increased, the energies went up, and we satisfied the boundary condition that the wave function had to go to 0 at the boundaries of the well. For the finite square well potential, we had a similar sort of thing, except for because this potential only went up to some v naught at negative a and above x equals a. We had those similar sort of sinusoidal type solutions inside the well. However, we had these exponential solutions outside the well where there was this finite potential. What's shown here is this is what we solved for the even solutions. The odd solutions were similar. There's sine instead of cosine there. But that was sort of the gist. We didn't get an analytical solution for the energies in this case because we couldn't solve it analytically. We had to use that graphical solution. But we were able to do this depending on how large this potential was and how wide our well was. We could change those things. As we lowered the potential and made the well smaller and smaller, we would lose some of these energy levels, right? Like if we brought this potential down to this level, this would no longer be a bound state. It would be an unbound state, and we'd only have 3 bound states inside that well. Likewise, we could keep bringing it down. One of the things we saw, though, is we would always end up with at least one bound state if there was a potential, no matter what the size was. So some of the things we can think about this, though, if we want to think about kinetic energy, so let's look at the infinite well case, right? We have these solutions and sinusoidal solutions increasing in energy as we go up. And if we take that energy eigenvalue equation in the position basis and put just the second derivative with respect to position on the left-hand side, bring everything else to the right, we get this. And this is essentially the curvature of our wave function, right? And if we look at this side, this is the total energy minus the potential energy. Now, if you remember classically, the total energy was equal to the kinetic plus the potential. So this means, this total energy minus the potential is going to be equal to the kinetic energy. So what we see here is the curvature of our wave function is related to the kinetic energy of our system, right? And we can see these in the graphical solutions in the well there. If our wave function has a positive value, the curvature is going to be inside the well, I should say. This energy is larger than the potential, so this is going to be a positive number. If the wave function is also positive, then the curvature is going to be negative. And we see that in all of these solutions, whenever the wave function is above 0, the curvature, it's curving back down towards the 0, right? And the higher the curvature, the quicker it's curving, the more the kinetic energy is. Likewise, if our wave function is negative, this kinetic energy in the bracket is still positive. That curvature is going to be positive, and we have the same sort of thing. Whenever that wave function is below the 0, it's curving back upwards. And as we increase the curvature, we have more and more kinetic energy. So essentially, these wave functions, the more sort of wiggles there are in them, the higher the kinetic energy is. We see the same sort of thing in the potential, in the finite square well potential. If we look, again, the Hamiltonian ends up being the same inside the well. That's greater than 0 because the potential is 0. If the wave function is positive, we're above the 0, and the curvature is negative, curving back down towards 0, right? Um, Again, more curvature, more kinetic energy, more sort of wiggles in there, the higher the kinetic energy of that particle. What about in the barrier region? All right, so we've just shown and discussed how inside the well we have essentially curvature relating to the kinetic energy, and sort of the shorter the wavelength or the more wiggles, the higher the kinetic energy of that particle. What about in the barrier? All right, in the infinite well, we had nothing going on in the barrier. That was sort of a special case that had to do with infinities. But clearly, in this finite square well potential, there is a wave function with finite value in penetrating into that barrier, right? Now, if you remember, the solution to the wave function in those regions was essentially q times x in the region back here, where x is less than negative a, and where x is greater than a, we had the opposite where this was negative qa. But in either case, if we just look at the absolute value of x, we're going to have this exponential decay with a decay constant equal to q, right? Which was given here, right? And that q is larger when the potential is really big relative to the energy. And we know, since we were looking, these are the solutions for bound states where that energy is less than that potential, that this is always going to be a positive number. So this exponential decay, hopefully you've all seen this before. You have exponential decay values. It starts with some value and it just decays exponentially. And you see this in the boundary regions here. The wave function hits the boundary at some value and then exponentially decays to 0. Another way we could write this, though, is e to the negative x over, we'll call it, so x over chi, some length, where we've defined chi equal to 1 over q. It's going to have units of length. We know that just because this exponential has to have unitless exponent. Where this is the distance over which that amplitude of the wave function decays by 1 over e, right? If when x gets to this is -1, so we end up with 1 over e is the amplitude of that wave function. This is proportional to 1 over the difference in the potential and the energy. You can sort of see this. When we're at a low energy, that number is big, and this wave function penetrates very little into the boundary. As that energy increases, how far that wave function makes it into the barrier goes up, and we have a larger penetration into that barrier, that potential at the edges of our well. We can also think, we've been looking at what happens as the eigenenergy changes. We can also imagine what happens if that constant V naught, the size of our potential, increases. And well, if that potential increases, Q gets much larger, or that penetration depth gets much smaller, and this penetration, the wave function is going to penetrate much less into that boundary. And if we actually take that to the limit of V naught goes to infinity, we recover what we saw in the infinite square well potential, where there's no penetration into that boundary. We should also think about what these wave functions mean, right? If you recall, that inner product of the wave function with itself is a probability density of where that particle can be, right? If you remember, you take the integral from -infinity to infinity of our wave function and its complex conjugate, that has to equal 1. We normalize over everything. We get the probability of that particle being somewhere as 1. But the point is, this wave function having a finite value in the boundary means there is a finite probability that if you were to measure the position of that particle in the boundary, you would find, there's a chance you would find that particle there. This is going to become very important when we talk about the process of tunneling. If you imagine a potential that looks something like this, and we have some wave function that decays, if that doesn't decay to 0, there's going to be a finite probability that although this particle never had enough energy to get over our barrier of V naught, there's a probability that it'll be measured, its position will end up on the other side. So this sort of barrier penetration, it's really kind of a weird phenomenon to think about classically. Classically, that particle is forbidden from making it outside of the plus or minus a region over here, right? This is the classically allowed region, and everything outside of it is classically forbidden. In quantum mechanics, we have this wave function penetration into the boundary that shows that there is a finite probability that that particle will be somewhere where it's classically forbidden to be. Another thing I want to touch on before we end this video is the properties of the Hamiltonian and what we just sorted out, just sort of as a refresher. If you recall, our observables are all Hermitian operators, and Hermitian operators have the property that their eigenvectors are orthonormal, right? Which means they're orthogonal. So if I take the inner product of any two different elements of that set of eigenvectors, I'm going to get 0. And if I take the inner product of any eigenvector with itself, I'm going to get 1, right? They also have the property that they are complete, right? Which means that the sum over all the outer products is equal to the identity, or put another way, the sum over all those projection operators onto each of the eigenvectors is equal to the identity. What that means is essentially we can write any state of our system as a linear combination of those eigenvectors, right? And we've used this throughout the course. If you even think back to our discussion of spins, we would, take the S sub z operator and we would use that z basis to describe all our generalized systems. We can do the same thing with this energy operator, our Hamiltonian, because it is an observable in a Hermitian matrix or Hermitian operator. So this is how we approach time dependence. If we had some time independent Hamiltonian, so some constant Hamiltonian for our system, this is what we do. Well, we know the evolution with respect to time is described by the Schrodinger equation shown here, and because that Hamiltonian, its eigenvectors form a complete basis, we can expand the state wave function in terms of those eigenvectors. So that's what we would do. We would just expand that state function in that eigenenergy basis, and then Schrodinger's equation becomes a very manageable differential equation that is just for the coefficients in that linear expansion, right? So we get these equations for our coefficients of our linear expansion of our state function. We can solve that. We did it. We ended up seeing this. So this sort of, those coefficients have this extra phase factor when we include the time dependence. And this sort of outlined our approach to how we solved for the time dependence of our system. We expanded our initial state of our system in terms of the energy eigenbases, and then we added these phase factors, these energy dependent phase factors to each term in that linear expansion to give the time dependence, and that gave us our time dependent state function. And once we had that, we can calculate the probabilities as a function of time, expectation values as a function of time, whatever we're looking for. So we did this a lot in the first sort of section of the course when we were still using the spin system as our model and Dirac notation. We've just switched to the position representation, And we spent the last few videos solving these two, this infinite square well and the finite square well, to get our eigenenergy or energy eigenvectors and our energy eigenvalues, so we can actually do this time dependence. We're going to do the exact same thing conceptually, but we're going to translate it into this position representation and start to see how things evolve with time. So in the next video, I'm going to work through an example similar to what's done in the textbook, where we're going to do just that. We're going to have an infinite well potential. We're going to have the state start in some initial state, and we're going to look at how we can go about seeing that time evolution, expanding that wave function in terms of our energy eigenbases, and going on from there. So that's what's up next.